Have you ever stopped to think about everyday things like your coffee cup or maybe a bagel? How they actually hide these really deep mathematical ideas?
Right, the shape itself tells a story,
Exactly. And what if matter, the stuff everything's made of, also has these hidden properties, these sort of topological features?
making them incredibly stable, even when things aren't perfect.
Precisely. So today, we're doing a deep dive into topological quantum matter. This is the stuff that won Phyllis, Haldane, and Kostfelis the Nobel Prize in physics. And our mission really is to unpack some of these, well, mind-bending ideas. We'll be leaning heavily on insights from Duncan Haldane's own Nobel lecture materials.
Yeah, and what's so fascinating, I think, is how these really abstract math concepts like topology, classifying shapes by holes, that kind of thing, suddenly became crucial tools,
Yeah.
absolutely essential for understanding how electrons and spins behave in these materials.
Okay, let's get into it. Maybe starting with something familiar like electrons and atoms. We learned about energy levels, right? Discrete levels.
Standard quantum mechanics, yeah, electrons fill them up.
But now, picture electrons moving freely, maybe on a 2D surface,
Yeah.
but with a really strong magnetic field thrown in. What happens then?
Ah, okay. So that creates something called Landau levels. Think of them as specific energy levels that electrons get forced into by the magnetic field. They start moving in little circles. And this is where Klaus von Klitzing made his huge discovery back in '85, the integer quantum Hall effect, the IQHE.
The Nobel Prize winner, right?
Yes, it's one. He saw that the electrical resistance jumped in these incredibly precise quantized steps. It looked almost perfect, like you needed to perfectly fine-tune the magnetic field.
But hang on, that sounds super delicate. Real materials, they're never perfect, right? They're messy, dirty, as physicists say, full of flaws. How could this perfect effect survive in a real sample?
That was the big question. It seemed impossible. The answer, which Bert Halperin first started to figure out, involves these one-way edge states.
One way. Like a one-way street?
Kind of, yeah. For electrons, they can only travel in one direction along the very edge, the boundary of the material. And these edge states are incredibly robust. They're topologically protected. Small defects inside the material just can't get rid of them.
So the messiness inside doesn't matter because the important stuff is happening right at the edges.
Exactly. These edge states essentially lock the energy levels in place, making the whole quantized effect immune to the imperfections in the bulk.
Okay, that makes sense. This robustness, this exact quantization, despite the mess,
Yeah.
it pointed to something much deeper. And that's where the TKNN paper comes in, from '82.
Yes, Thouless, Komodo, Nightingale, Denny S. They developed this amazing formula for the Hall conductance. And the key thing, it didn't depend on any delicate fine-tuning.
No fine-tuning needed.
Right. And then a year later, the mathematical physicist Barry Simon recognized their formula. He realized it was actually calculating a known mathematical quantity, a Chern integer, which is a topological invariant. It's like counting the number of holes in a shape, the genus.
Like our coffee cup has one hole, the bagel has one hole. Topologically, they're similar, unlike, say, a sphere.
Exactly. It's a fundamental property of the whole shape. Doesn't matter if you stretch or bend it a bit locally. Simon realized this mathematical robustness was the physical reason the quantum Hall effect was so stable against imperfections.
Wow. So abstract math explains real-world physics. Okay, so what did this mean for finding new materials? Did TKNN suggest you could get this Hall effect without needing that huge external magnetic field?
Precisely. That was the huge implication. If it's about topology, maybe the magnetic field isn't essential. And in 1988, Haldane proposed a theoretical model, what we now call a Chern Insulator. It was a model like on a graphene lattice that showed a quantum Hall effect with zero net magnetic field.
Zero field. How?
Just by cleverly arranging things to break time reversal symmetry internally, you could argue it was the very first topological insulator.
Amazing.
Yeah.
And later, Kane and Mayle found a version that didn't even need to break time reversal symmetry.
That's right. In 2005, they found a time reversal invariant version, opening up even more possibilities.
So while all this was happening in 2D systems, Haldane also made another huge discovery, but in simpler one-dimensional systems, right? Back in '81, the spin chains.
Yes. And there's a funny story there about it being a lost preprint for a bit. It didn't get much attention initially, but what it showed was revolutionary. It revealed that quantum spin chains, just lines of interacting spins, behave fundamentally differently depending on whether the spin is an integer, like spin 1, or a half integer, like spin 12.
Which went against what everyone thought at the time.
Completely. For decades, the assumption was they behaved similarly. Haldane showed integer spin chains have an energy gap, a fundamentally different state of matter, while half-integer ones don't.
What was the underlying physics? How did he figure that out?
It came down to quantum interference. Basically, interference effects between different quantum paths canceled out in a special way for half-integer spins, leading to a gapeless state. But for integer spins, there was no such cancellation. This led to this new gapped phase, which we now understand as a symmetry-protected topological phase, or SPT phase.
SPT phase.
Yeah, there's a nice model, the AKLT model, that helps visualize it. You can think of each spin 1 as being made of 2 spin 12s. In the chain, they mostly pair up, but at the very ends, you're left with an unpaired spin 12.
Ah, like an edge state again.
Exactly, a topologically protected edge state, this time in a 1D spin chain.
Incredible. So, from electrons doing their circular dances in 2D to spins lining up, or not lining up, in 1D chains, this whole deep dive shows how topology, this abstract math, unlocks these really surprising and robust quantum behaviors in materials.
Absolutely. These early discoveries, often starting from what seemed like simple toy models, completely changed the game. They launched the entire field of topological matter, and that research is still pushing forward, looking for new materials, potentially for quantum computing, all sorts of things.
It really makes you wonder, doesn't it? What's something in your own world, maybe something you see every day, that if you look closer might reveal some hidden, unchanging property you just never noticed before? Definitely something to think about. Keep exploring.